trying to decide. We have a couple of integral equation problems, short ones that we'll do in class in evening sessions, which we'll do next week. And then there's also, I guess, some discussion about the final project. I think if you all have opinions about this, you should express them to Professor Wang. We will take them under advisement. But we'll try to, we're very mindful of not packing a lot of work in the last week of classes. So for today, I'm going to talk about quadrature, and for those of you looking for the video from yesterday's Monday's lecture on it, it's getting there. I have to compress it, I guess, before I can post it. But it should be up by tomorrow at the latest, and we'll have the video for this one too. The camera's running at the moment. I haven't officially asked for any of you for signed disclosures. I don't think anybody of you show up on the video that you ask a question. Your voice might be on the video. If you have objections to this, certainly feel free to mention them to me and figure out something. Okay, so we're going to talk about numerical quadrature. And many of you may have seen Gauss. How many of you have used Gauss quadrature? How many of you have seen an analysis of how the formulas are derived? A couple. Okay, so for those of you who have seen this before, this won't be new. And for those who haven't seen it before, I guess it will be, which is not exactly a very informative statement, but there it is. So I'm going to go through a little bit of it. And the reason we're going to talk about quadrature and the ways in which you derive quadrature formulas is it will really lead into the next lecture, which is how you take these ideas from quadrature, which you may or may not have seen before, and use them to actually come up with methods for solving integral equations, and give you a method that's really extraordinarily effective in 2 space dimensions, and doesn't necessarily generalize that easily to 3 dimensions, although there have been some recent improvements in that. So part of the reason we're talking about quadrature is to fill in some background in case you're missing it, but partly it's because it's going to lead us right into very effective ways, or one of the most effective ways of solving integral equations in 2 space dimensions. All right, so what do we mean by quadrature? And that is we're going to approximate an integral which is, of course, just the area under a curve. And we want to do it with some formula. That is, we're going to use values of a function and weights. So if you're doing an integral from 0 to 1, which we'll probably be doing, we don't have the integral in that because I'm just going to integrate this f of x dx. So I'm trying to get the area under the curve from 0 to 1. And I'm going to approximate it with this boxcar of height f, and I evaluated it. So that's not a very difficult quadrature scheme. It's an approximation. And we can come up with better approximations. And the obvious one is, well, if it doesn't work to approximate your function with 1 boxcar, maybe 2 boxcars would be better. So I'm sure all of you have learned this in calculus, that it would be better to use more boxcars when you do the Riemann sum. But before we do that, let's talk a little bit about just this boxcar and what it's accurate for. So the extraordinary thing about that 1 boxcar is, of course, it's exact for a function that's a constant on the interval 0 to 1. It's also exact for anything that's a constant or linear. So it's actually a single point quadrature scheme. It's a lot more powerful than you think it is, but in fact, it's more powerful than if I use 1 point on the end. So suppose I look at these functions that are linear, and I want to get the area under the curve, and I have 3 choices about how to approximate it. I could use a point at the beginning of the interval. So I could use f of 0. Or I could use, for that same linear function, f of 1. to say immediately about both these methods? Do they work if the function is constant? If f of x equals a constant, are these formulas exact? All three. So we could sometimes call this one the midpoint. And both of these are called endpoint methods. The endpoint methods are exact. If it's constant, what if f of x is equal to ax plus b? Which of these formulas are exact? The midpoint or the endpoint? The midpoint. Midpoint only. So we could sometimes, if we want to be formal about it, we could say the endpoint methods are good for polynomials of order 0. And the midpoint methods are good for polynomials of order 0 and order 1. That, in fact, that idea, that simple idea, thinking about what kind of polynomials, functions, you could exactly integrate the area under the curve of, is the heart of everything you're going to learn about quadrature. So everything else I'm going to tell you is an extension of that idea. We look at quadrature formulas, and we're going to ask questions about how high an order of polynomial we can exactly integrate. And that's going to tell us some way of comparing these methods. So in this very simple setting, we're going to start talking about a lot of things about these polynomials. But just keep in mind that simple idea, that we're going to try to come up with methods that can accurately integrate higher and higher order polynomials, and that's how we're going to assess which method is better and which method is worse. So if we want a method that's more accurate than the midpoint method, if our function is not a constant or a linear function, it's not a 0th or first order polynomial, then we could break it up into 2 boxcars. Does that accurately integrate a higher order polynomial? That is, does that, if I use 2 boxcars in the midpoint method, can I exactly integrate any quadratic? What about if I used, instead of the midpoints for these 2 boxcars, what if I used endpoints? Would that exactly integrate any quadratic? So, what about a linear function? If I use 2 boxcars, will the midpoint method exactly integrate a 0th and first order polynomial? If it's a straight line, I break this up into 2 boxcars. Will the midpoint method still integrate the linear case? Yeah. Exactly. What about if I use the endpoint method? Will it integrate a linear one exactly? No. So breaking up into more boxcars, more sections, doesn't necessarily get you a higher order polynomial unless you try to arrange for it. So that's another thing we're going to worry about, which is what should we do if we use lots of points? And just using equal weights on the 2 points may not be the best thing to do. Although, surprisingly, in important cases, it is in fact the best thing to do. All right, so but this is going to be our general problem. We're going to imagine, well, we can evaluate the function. We're presuming that you can evaluate the function. You don't want to evaluate the function too much because the function may be expensive to evaluate. It might be the result of some complicated calculation you're doing. It may be something as simple as evaluating 1 over r, 1 over distance. But usually you want to minimize the number of evaluations you have to do and get the best answer you can get. And you have 2 degrees of freedom. And I want to keep in mind these 2 degrees of freedom. So we have, or I should say, 2 types of degrees of freedom. The first type is the weights for each point. For each of the boxcars, how much do you weight that point? And the second type is where to put the points. looking at the midpoint in these two endpoint methods, we pick the weight of 1. We only have 1 point. So weights, the freedom to pick weights doesn't really come into it. But we can see already, even in a 1-point quadrature scheme, that degree of freedom of where to put the weights, where to put them, that's an important degree of freedom. And if we use something like a midpoint rule for each one of a collection of n boxes, we would put 1 over n as the weights, all weights being the same. And each of the test points would be in the center of each of those boxcars. So that's a general midpoint formula, and you might ask the question, is that the best thing to do? Could you put the points in different locations? Could you use different weights? So if I have an n-point scheme, how many degrees of freedom do I have? So I've got n boxcars. I can pick n points to n places to put I can make the boxcars thicker or thinner, so I can put the points anywhere. So I've got n points to place. What about the weights? Do I have n degrees of freedom in the weights? How many degrees of freedom do I have? What do I know about the weights?
They all have to sum to 1.
Why do they have to sum to 1? Suppose f of x were constant, 1. Then that formula should produce exactly the right interval, which would be 1. So that's why the weights have to sum to 1. But that idea that the weights have to sum to 1, when you think about that, yeah, of course, because it's got to integrate the constant function exactly. But that's like saying the weights have to be such that the 0th order polynomial gets integrated exactly. We get another condition on the weights so that we'd exactly integrate a constant and a first order polynomial. So we're going to think a little bit about that. So there are 3 different methods we could look at. We could use one method, which is an endpoint method. We use the beginning of each of these boxcars. A second method, the one we've been looking at mostly, this midpoint method, we pick off points in the middle. And the third one is sometimes referred to as the trapezoidal rule. And why is it called the trapezoidal rule? Because you can't see it here, because it's not clear enough in the picture. But each of these things are trapezoids. They're straight line approximations to whatever that function is. Which is the best one to use? Is the trapezoidal one better, or the midpoint one? Midpoint. Say again?
The midpoint.
So it turns out the midpoint one is better. The trapezoidal rule is it's putting a straight line between points. So I'm going to draw a picture of that so you can see why. So imagine I have a curve like this and I do it with the trapezoidal rule and I just exaggerate it. So these are going to be my trapezoids. So I've got 2 trapezoids. And I have an error. For that same curve, what would the midpoint rule do? Here are my 2 boxcars. What does the midpoint rule do? It's going to use the points where? If I use the midpoint rule, what value am I going to use? I'm going to pick a middle point. And that means my midpoint rule looks like this. So by looking at these 2 pictures, it should be obvious to you that the midpoint rule is going to be better, right? Is that obvious? Which error is smaller? If I drew a slightly different curve, could I get a different answer to this question? Maybe. If if I happen to pick a piecewise constant curve, my curve is this, the rooftop, then trapezoidal and midpoint will both get exactly the right answer. After that, all right, so it can be a little difficult to decide some of these questions, even in this simple setting, about error. And so we need some more formal methods to think about it. And it also turns out we need some tricks, well, numerical insights that will help us actually come up with ideas about where to put points and how to set weights. All right, so for the moment, we're going to worry about a general quadrature formula where we think of picking the weights and picking the evaluation points, and that will give us 2n degrees of freedom. Where the way you normally think of, well, wait a second, don't the weights have to sum to 1? That's a constraint. And we're going to see if we want, that's a constraint to make sure that we get the exact answer for a constant. But it's one of a whole family of constraints. So we're going to think about having these 2n degrees of freedom. But we're going to very quickly see that we're going to need to put some constraints on it to try to get good accuracy. So we're going to pick the evaluation points, and we're going to pick the weights. So how should we do that? So we already started talking about the key idea. What I said was the key idea. The polynomial. Right? We are going to say, I have this function, and I'm going to say I can approximate it well with a polynomial up to nth order. And what we're going to try to do is to pick the points and the weights so that it accurately integrates any polynomial up to as high an order as possible. So we can, by picking the points and the weights, because we have 2n degrees of freedom, we can actually come up with points and weights that will exactly integrate any polynomial up to the nth order, where the nth order is 2n minus 1. Why 2n minus 1? Where does the minus 1 come from? So how many coefficients does an nth order polynomial have if I write it this way? Well, because I wrote it from A0 and A1 all the way to AL. You know, if you're a programmer and you write software a lot, count from 0, then of course, you know, that's L plus 1 coefficients. So that's where the 1 is coming from. The nth is the order, but the number of degrees of freedom is L plus 1. So we can get to an nth order polynomial means we have L plus 1 coefficient suite of that polynomial, and that we're going to match to the degrees of freedom in our quadrature scheme. So we have 2n coefficients we have to find, and that means we can match 2n coefficients of a polynomial, and that means L plus 1 is equal to 2n, or L equals 2n minus 1. Okay, so that should be easy. Right, so how are we going to do that? I've got points and weights, and I want to make sure that we pick the points and the weights so we exactly integrate any polynomial of order up to L. How do I figure out what where those points and weights are? Can I write down a system of equations and solve it? Do I just go ahead and do that? So we're going to talk about that in a little bit. But I wanted to say something about the error estimate. Because these methods, when you do this, doing the midpoint rule with boxcars, or doing something like this, where you pick the points and weights to exactly integrate as high an order polynomial as possible, they have very different convergence properties. The Gaussian quadrature, or any quadrature scheme based on trying to match as high an order polynomial as possible, has what we call spectral convergence. So normally, when you refine a discretization, you figure, all right, if it's in a method of cubic order method, you might expect that if I half the number of the step size in my discretization, then maybe the error goes down by a factor of 8. Or maybe I have a second order method, in which case the error goes down by a factor of 4. Or a first order method goes down by a factor of 2. You have this idea that it is the refinement. I take the discretization, I use twice as many points, I get twice as much accuracy. If it's first order, 4 times as much accuracy. If it's second order, 8 times as much accuracy as third order. What do you think you get with Gaussian quadrature? So what that formula means, although it's a little hard to tease out from the factorial way it's formally presented. It says that for every point I add, the accuracy increases by a factor of 2. So it's not going down like 1 over, it's not going down linearly or quadratically or cubically with the number of points. It's going down exponentially fast with the number of points. So imagine how many, if you want to get 16 digits of accuracy, 2 points gets you 1 digit, then 3 points gets you 4 digits, 4 points gets you 8 digits, 5 points gets you 16 digits. So when we're talking about these methods, we're talking about methods that have extraordinary rapid convergence, but they count on certain properties. And we're going to come back and talk a little bit about what those properties are, because unfortunately for the integrals we use in this class, they violate the properties for which that's true in many of the cases, but not all of them. And we'll look at some important ones that show up in 2D. All right, so let's look at an example. So it's, I can say, all right, what does spectral accuracy mean? What does it really look like when we're talking about this? So I'm taking the sine function. I'm going to do the sine function and integrate it with a quadrature scheme, because we can exactly integrate the sine function. We'll learn how to do that in calculus. And what's true about the sine function? Why do you think I picked that function? So do any of its derivatives go to 0? Is there any polynomial that exactly describes the sine function? No, if it did, then I could differentiate the sine function a certain number of times, and at some point the derivatives would go to 0. But that never happens, right? If I differentiate the sine function and differentiate, I get sine, cosine, sine, cosine, sine, cosine, so sine, cosine. Derivative never goes to 0. So it's not described exactly by a finite order polynomial. And it gives us a chance to look at the convergence properties of a method for which we actually know the exact answer. So this is the error analysis, and this is looking as the point, a log-log plot of error versus number of points. And if you look at this scheme and say, well, what happens when I increase the number of points by an order of magnitude? What happens to the error in this plot? So an order of magnitude increase in the number of quadrature points, meaning I break it up into an order of magnitude more sections, an order of magnitude more evaluations. How much does the error go down? Well, you look at it, an order of magnitude on the bottom curve looks roughly like how many orders of magnitude on the side? So we're looking at a plot of error versus number of points. 2 looks sort of like, and that would be a second order method. You increase the number of points by a factor of 10, and the error goes down by a factor of 100. That seems pretty good. It means that, with 1,000 points, 10,000 points, we can almost get machine precision. So that's not a quadrature scheme. That was, which of these 2 methods do you think was the midpoint rule or the endpoint rule? Yeah, it turned out it was the midpoint, because the endpoint rule doesn't have such rapid convergence. Now, I'll come back if there's time and talk a little bit about the Taylor series algorithms, but I just want to make a point about it because it's the heart of why the methods that we're using work. If I do a Taylor series expansion of a function, as long as it has, it's infinitely continuously differentiable. So sine functions are infinitely continuously differentiable. Then I can write down the Taylor series expansion for f of x at every point x. And that means up to a Taylor series residual, I can write down a polynomial representation of f of x. And when I do a quadrature scheme that's exact for that polynomial, it means we'll pick up that order of the Taylor series, but we'll miss out on the remainder term. And the remainder term for the Taylor series expansion is this thing that has a coefficient in front of it that goes like the factorial, and also with the derivative. So looking at this Taylor series expansion, it says, if we're going to do something that's exact for polynomials, for progressively higher order polynomials, we want something for which the Taylor series remainder theorem works. It means we want something that's infinitely differentiable. And what has to be true about the derivatives? These derivatives are going off to infinity as you differentiate more and more and more, that's not so good. If they go up, if the derivatives go up faster than the factorial goes down, then these methods aren't going to be very good. So we want things that are smooth and for which the derivatives don't go up. And if we do that, then we get this incredibly rapid convergence, and then it's worth looking at. Well, I saw anything. So maybe I'm going to skip ahead and show you the plot, and then we'll come back and look at the here. All right. So what I showed you in the first plot was the simple quadrature scheme, the midpoint rule. I'll come back and do all the slides in the middle. I just wanted to show you the result at the end. Simple quad. To get to machine precision, that midpoint rule would take 10,000 points. For Gaussian quadrature, in about 11 points, you can get to machine precision. So we're not talking about, oh, it's 2 times faster or it's 4 times faster. If you're looking for accuracy close to machine precision, that is high accuracy calculations, you're talking about, instead of having to do 10,000 points with a midpoint rule, you're talking about doing 11 or 12. And all you have to do is to figure out what the good weights and evaluation points are. And we'll look at those in a little bit, but I want to go back and talk about how we get there. So we have this idea that any smooth function, infinitely differentiable function, can be described by a polynomial. And if we can pick up that polynomial, then the remainder term is very small, and the higher the order of the polynomial, the smaller this remainder term is, and it goes down really, really fast with order. So how do we do that? So we're going to produce this exactness condition, and we're going to do it on this unit integral, just so we have an example here. We're going to try to exactly integrate a polynomial, an nth order polynomial, and we're going to try to pick the points and weights so we exactly integrate that nth order polynomial. And we can use a lot of properties of this integration. So let's have a look at this. I take an nth order polynomial. I write out what that nth order polynomial is. It's this integral from 0 to 1 of a0 plus a1x plus a2x squared, etc. And I can write it down as this sum of quadrature weights and points. Remember, we're talking about taking this nth order polynomial. So we have this thing, PL of x, on this interval from 0 to 1. And we're trying to figure out where to put points. Well, I've got x1 through x of n. These are our points. And then we've also got, for a point xi, a weight I that we're going to multiply by PL of xi. And we want to pick out these points and weights. So when we're looking at the integral from 0 to 1 of PL of x dx, that's exactly equal to this sum from I equals 1 to n of wi PL of xi. So we want this to be exact for all polys up to L equals 2n minus 1. So we now need a strategy for figuring out what those are, and we can start to make headway with that strategy by just writing down the polynomial pulled apart into its different, what are called monomials. So we have the constant monomial, the first order monomial, the second order monomial, and then all the way to the nth order monomial. And monomial, the mono there just means there's only one. You know, if we're talking about an nth order monomial, we're just talking about x to the L. There's no x to the L minus 1, x to the L minus 2. And why should we do that? Does that help us generate a system of equations for these points and weights? Suppose A1 through AL were equal to 0. Does this formula have to work for that polynomial? It's now A0 times x to the 0th power 1. Does this formula have to be exact for that? Yeah, all right, one condition. I throw away that term, and I throw away all the ones A2 through A and A0, and I'm just left with A1x dx. So that's my polynomial. I set A0 to 0 and A2 through AL to 0. Does this formula have to be exact for that one? Yeah, sure, because it has to be, this formula has to be exact for any Lth order polynomial. So each of those terms gives us one constraint. The A0, the 0th order polynomial, the 1st order polynomial, the 2nd order polynomial, each of those gives us a constraint that we can use to figure out the points and weights. In fact, it gives us exactly the number of constraints we need, right? Because we're going to set L equal to 2n minus 1. So that means we have 2n minus 1 degrees of freedom, or 2n constraints for 2n degrees of freedom. And then what we want to be true is that given this exactness constraint, we can say then if we take the monomial, the x to the L plus 1 monomial, and take the difference between that and integrating the with this weights and points, that error is going to be something like the remainder term in the Taylor series expansion. And so I'm not going to do that too formally here. It's easy to find in basic textbooks, but that's the intuition to have in mind. That when we do this, if we match for all the way up to Lth order polynomials, what's left over, that remainder term has to be really small. All right, so can we do this? We have 2n degrees of freedom. We have 2n constraints. We could just set up the nonlinear system. Right, there it is. Right? So there's our set of constraints. Right, we just have to make sure that the integral of the constant, the linear term, all the monomials, that sum formula works for every single one of those cases. We have 2n equations in 2n degrees of freedom. Is that a linear system of equations? Can we solve that? What do you think? What are our unknowns here?
UI and X.
Yeah, you've got the points. Where are the points? And what are the weights? So it's not a linear system of equations because the terms in the equations are products of your unknowns. This is the nonlinear system of equations. So what method you use to solve a nonlinear system of equations? F-min-con. Sorry, for those of you who use MATLAB. I don't know what it is in Mathematica. It's F-min-con. You could try it. Right? You could just stick these equations in. All you have to do is evaluate those integrals and use them as the and send it into F-min-con. See if you can come up with points and weights for it. It's going to have trouble. To do it this way, to set up the nonlinear system of equations, so we can write this nonlinear system in a kind of geometric way that helps us understand what's going on. We can write it as a matrix of whose columns are these evaluation points to for all the different points. We can write down the quantities we would get for each of the points, the x to the L. So this last row corresponds to dealing with the x to the L polynomial. And the first row is the constant polynomial. And if you look at that system of equations, you should be able to see something almost immediately. What's true about those rows? Right? Each of those rows is looking at a polynomial. So this is x1 through xn. These are points between the intervals 0 to 1. And the last row is taking each of those points to the nth power. The first row is taking each of those points to the 0th power. Are those rows very different from each other? So we can solve this system equation. We could use Newton's method. And if you've taken 6336, then you know you've done some with Newton's method. You can write this down, but we're going to try to develop some intuition about what's going on just by thinking about that matrix that involves the x's. Anybody know what that matrix is called? Ever seen this one before? Yeah, this is what's called the van der Waals matrix. So since you knew what van der Waals was, what can you tell me about van der Waals matrices? So it isn't singular, the van der Waals matrix, but it gets progressively less well conditioned as L goes up in order. And a quick way to see that is to think there's the constant polynomial, the linear polynomial, all the way up to high order polynomials. This is what we get for the Jacobian and Newton's method, but that's less important than thinking about what those rows look like. So this is a picture of a plot of the rows. Just take each row and plot its points from 0. So these are this is the x1 through xn along this the x-axis, and then the value of the monomial for each of these points. And let's look at what happens. The one that's all 1, that's the constant term. That was the first row. The second row is the x. Right? The second row is x1, x2, x3, x4, etc. It's just back here. The third row is the quadratic. The fourth row is the cubic. Fifth row is the quartic. Sixth row is the quintic. What's true about those functions? Do they look like they're looking more and more like each other the higher I go up in order? So in the limit, as L goes to infinity, what are these functions going to look like? So we've got the constant, we've got the linear, we've got the quadratic, we've got the cubic. What's the linear? What's the limit as the power goes to infinity? What will this function look like? Anyone know what it'll look like here?
Like a step function.
Yeah, after a while, they're all going to look like this. Because all the points that are less than 1, you take them to a high enough power, any number less is magnitude is less than 1, you take it to a very high power, it becomes, it's 0.99, and I take it to the millionth power, it's 0. So eventually, they're all going to look like this white function. They're all approaching the same thing. That means this matrix, as I make it longer and longer, try and go to higher and higher order, means the rows are starting to look more and more like each other. And that means that matrix is getting progressively worse condition. It's approaching a singular matrix. So you can try these out in MATLAB, and you can see how many points you can get away with. It turns out about 13 or 14 rows you run out of numerical precision in MATLAB. So you can do these things in double precision to about 10 order, and then MATLAB has problems. So I told you there's this great method for getting machine precision accuracy, only to figure out what the points and weights are, you need to be able to do calculations at much higher than machine precision because of the van der Waals matrix. So, it was fun, and it's a nice theoretical thing, and it's not very practical, and nobody really uses these things. And, maybe we can stop early. But no, we can fix this. How? Why did I use the monomials? Why did I choose to use as my test polynomials? 1, x, x squared, x cubed, x to the 4th. Is that a good set of polynomials to use? They're monomials. It's nice name, monomial. They look simple. They only have one term. They're easy to construct. They have a lot of appealing features. It makes it very easy to generate these matrices, for example. But what property don't they have? Well, they start to look an awful lot like each other as you go to high order. So if I told you, well, I have this set of vectors, and they're starting to look more and more like each other as I get more and more of these vectors, and I kind of want to come up with some way of figuring out how much of each of these vectors to use. What scheme would you do to try to be able to tease those different pieces apart? So I have a set of vectors, and they're almost linearly dependent, and I want to turn them into something that is as close to orthogonal as possible. What scheme would I use? So I have a set of columns of a matrix, and I want to make the columns orthogonal to each other. What do I do? same person who invented this algorithm invented a kind of cracker. Graham-Schmidt, you don't remember Graham-Schmidt orthogonalization? No. All right, so then we're not going to worry about the way we calculate these polynomials. But let's for a moment assume that we could come up with orthogonal polynomials. We're going to pick some other set of polynomials. We don't like the monomials. We're instead, because the monomials start to look like each other, and we're going to decide that instead we're going to come up with polynomials that have a certain property. So instead, we're going to try to come up with polynomials that are very different from each other. And we're going to define very different as something like this. We have a ci of x, a cj of x, integrated over this interval from 0 to 1. And we want it to be equal to x, and we want that to be equal to 0 if I is not equal to j. This is orthogonality. So you've seen that a little in trying to construct basis functions that are orthogonal to give you better condition systems when you do a basis function-based discretizations of PDEs. But you also have it in a very much simpler setting. We're doing the same thing. If I took these polynomials and sampled them, I would get a vector, and then we're still talking about trying to make these two vectors orthogonal to each other. So it doesn't matter whether you think of this as a polynomial, two polynomials we want to make orthogonal to each other, or you think of representing them as a function and with points, and we're trying to say the two vectors, like the picture we drew here. If we think of these as vectors, we're now going to end up with vectors whose inner product is going to be 0. And now how are we going to construct those polynomials? Well, I'll come back. Let's pretend we have them first. Suppose we could construct polynomials. So here's one, right? So is the polynomial 1, all ones, and the polynomial x, are they orthogonal to each other? If I take the inner product of 1 and x and integrate it from 0 to 1, are those two orthogonal to each other? Not at all. Can you give me a polynomial that has a first order and a 0th order term that is orthogonal to 1? So I have 1, and so give me a polynomial that involves x that is orthogonal to 1. 1 minus 2x. All right, so I'm going to flip the sign of that. So suppose I wrote down, if I have x and I'm going from 0 to 1, and I want it to be, its inner product to be 0 with 1, what am I going to subtract off? So what you said is exactly right. You can see you said it. But I'm going to scale it slightly differently. I have x, it goes from 0 to 1. And I now want it to be orthogonal to 1. And I take the inner product of the constant with something that's linear. What do I want to make this linear function do so that the inner product of these two is a constant? Excuse me, 0. What should this function be? It's got to have the x in it because it's got to be monomial. What should I do with it? All I got to do is shift it somewhere. Where? If I take this point at a half and make sure it goes through the half, are these two orthogonal to each other? So I got this one, the second one, by taking the 0th order polynomial and subtracting some fraction of it off the first order polynomial. So now you can do that scheme. You can do a second order polynomial by starting with x squared and then subtracting whatever it takes to make the x squared orthogonal to the first order polynomial and subtracting off whatever makes it x squared orthogonal to the constant polynomial. So we can construct polynomials this way. But I'm not going to worry so much about that at the moment. Let's presume that we can figure out how to do that. So suppose we recast our exactness constraint. with these orthogonal polynomials, where we can't just pick any polynomials. They have to have, the zeroth order polynomial has to have the monomial, the x to the 0 monomial. The first order one has to have the x1 monomial, and the second order one has to have the x squared monomial. But other than that, they can have whatever weighted combination of lower order monomials to make them orthogonal to each other. So we imagine then saying, all right, we started out with n monomials, or excuse me, 2n monomials, or the zeroth order one plus all the way to order 2n minus 1 in monomials. So we have our 2n constraints starting from the constant term all the way to the nth order polynomial. And we're going to replace those monomial constraints with constraints using these orthogonalized polynomials. It should be, because it should be good enough. I mean, any set of polynomials, as long as we can guarantee that we can write down any polynomial as a weighted combination of this orthogonal set, which you can. You can certainly, each of these is involving monomials, and we can put them together in ways to make the whatever polynomial we want. So we have certainly covered our constraints, but now we're putting it in terms of these orthogonal polynomials. So an nth order polynomial still has to have x to the nth power, but it can have any of the lower order terms, and because of that, we can represent any polynomial with a weighted combination of these orthogonal polynomials, and we can rewrite our constraints. Is this going to make our problem any easier? We still have 2n constraints. Are these now constraints of this now, are they now linear? Well, you know, because I put the x's inside these c functions. So doesn't that make the problem linear? No, of course not. You may be a little more hidden, but they still have the products of weights times polynomials. They're just more complicated polynomials. If anything, it seems like it makes it harder, because the original ones might have the L constraint had one weight times only a coefficient times x to the L, and now it's got all these other terms, the x to the L minus 1 and L minus 2. Seems like we're making it worse. All right, so if we have these orthogonal polynomials, and this notion of orthogonal for polynomials is, we say that inner product of the two polynomials is equal to 0 if they're of different order. And we sometimes use this inner product notation, or we use rectangular brackets, but it's the same idea as taking two vectors and looking at their inner product. And if we sampled the polynomials and constructed the vectors that way, it would turn out to be identically the same thing. Or if we did this by quadrature, well, we'll get to that. So imagine now we do the following. We rewrite the exactness constraints, and we do it for the first half of the terms, what we'll call the lower order terms, from 0 to n minus 1. We'll write those in terms of these n minus 1 orthogonal polynomials. And then for the higher terms, we're going to write them a little bit differently. Right? These are the terms that have to do with Cn through C to the 2n minus 1 polynomial. So we've got the lower terms from 0 to n minus 1, the higher terms from n to 2n minus 1. And we're just breaking them in half. Now these higher order terms, we don't have to generate these additional polynomials, the nth order and the 2n minus 1 order polynomial. We could do something different. We could instead say, well, if I want an nth order polynomial, an n plus 1 order polynomial, or an nth order polynomial, I could take c to the n, and I could just multiply by c of 0. Right? That's still, c of 0 is a 0th order polynomial. If I multiply it by an nth order polynomial, it's still nth order. But when I get all the way up to a 2n minus 1 polynomial, I could have written it down as the product of the nth order polynomial times the n minus 1 order polynomial. Will this product still have a term that's x to the 2n minus 1? Right, the highest order term in the Cn polynomial will be x to the n. The highest order term in the Cn minus 1 polynomial will be x to the n minus 1. The product of the two will be x to the 2n minus 1. Right, that's all we're using. And we also know that the products are independent of each other, because we know that when we do, because we know something about Cn times C0. So these are different from the lower order polynomials. So now we have yet another way of writing our exactness constraints. And this is the really amazing thing. If we write our exactness constraints for the high order polynomials, and we're using orthogonal polynomials, then these inner products really should all be 0. Because if we integrate, right, these terms are all 0. Because they're orthogonal polynomials. I'm using products. So the actual integral we're trying to match. But that doesn't mean our quadrature scheme produces 0. But it gives us a very simple thing to evaluate. Now the question is, how do we make sure that our quadrature scheme produces zeros? So we know for the high order terms, the integrals we're using to test all have the integral 0, because they're integrals of the products of orthogonal polynomials. Cn times C0, Cn times C1, Cn times C2, all the way to Cn times Cn minus 1. But we don't know if the quadrature formulas give us 0. Is there a way we could ensure that those to be 0? I mean, I've got this 0 up there. Take the points to be the roots of the nth order polynomial. That is, I have Cn. It's an nth order polynomial. It has terms from A0, A1 plus A1x plus A2x squared, etc. That's what we're going to have to do. So we want Cn of xi to be equal to 0. Or if we write down what Cn is, Cn of x is equal to A0 plus A1x plus A2x squared all the way to A to the n, x to the n. And we're going to take this polynomial, and we're going to find its n roots, or its n xi's. That's what we're going to do. If we do that, it means we've satisfied the higher order terms immediately. We don't have to do anything. It says, here's our quadrature scheme with we've got n weights. Doesn't matter what the weights are. As long as we use these n points, these roots of the nth order orthogonal polynomial as our evaluation points, then I don't care what the weights are. I'll always satisfy the high order and exactness constraints. For free. Amazing. Well, I thought it was amazing. I remember learning this for the first time, and I was astounded. Who thought of this? Gauss, who thought of almost everything. So, how do we figure out what the weights are then? I mean, does it matter what the weights are? Can we use any weights? It doesn't matter, the weights, it doesn't matter what we pick for the weights. We're always satisfying the high order constraints. We still have those pesky low order constraints though. The ones having to do with C0 through Cn, we still have those. Right, so, but those, because now we know where the evaluation points are. We have the evaluation points because we know we got them from the roots of this polynomial. And then once we know those evaluation points, we can set up the linear system and solve for the weights. And with these weights, we'll exactly satisfy the low order constraints. So what do? We find n orthogonal polys. The xi's equal the roots of Cn of x. And then the weights linear solve. That's it. That's all we have to do. Now the question is, okay, so how do we get these orthogonal polynomials? And what about this linear system? Is this linear system well behaved? What are the rows of this linear system? The first row is the zeroth order polynomial. The second row is this first order polynomial that formally the polynomial is orthogonal to the zeroth order polynomial. So that row is like a picture of the polynomial. So the second row is almost orthogonal to the first. And it turns out to be precisely orthogonal with these points, but that's more subjective than I was interested. But each of these rows now corresponds to sampling of a polynomial that's orthogonal to the one in the row above it. So this linear system is like to be well conditioned. Sorry, did you have a question? So that's it, right? Did we make the problem linear? I mean, when I started writing down at the beginning, I said, well, we could set up this nonlinear system of equations, and we could use Newton's method to solve it and come up with the points and the weights. And I said that was going to be helpless because of the ill conditioned matrix. And where did that nonlinear thing go? Is it still here? Is the problem still nonlinear? Yeah.
We need to solve for the roots.
Yeah, it's here. All right, finding root finding is nonlinear. But what property does it have which makes it very appealing for us to use for quadrature schemes? Why is trading in that big nonlinear system to solve for just finding the roots of a high order polynomial a really good idea? Because this is someone else's problem. Right, there's in MATLAB they have something that counts roots of polynomials, and we'll find all of them for you. Yeah, there are all these. That's a little glib. What we've done is to turn our problem of calculating quadrature points and weights into one for which they know how to numerically compute solutions, roots of polynomials, and we're using that to solve for our points and weights. But the nonlinear problem hasn't gone away. It just means that we have turned it into one for which there was already a lot of work on making good procedures. We're really counting on the fact that somebody else has already solved that problem, and we just used it in this case. So we haven't taken the nonlinear problem out. We have just decomposed them. So we have this nonlinear part of the problem is encapsulated in the polynomial roots, and then we have a linear solve. Yep.
Is it possible that has like complex roots, or would you construct the polynomial so that it?
So the orthogonal polynomials, so you have to have ones for which the roots are going to be real. So yeah, you have to. That is an issue. And if you use polynomials that are orthogonal over, say, an interval from -1 to 1, like the Chebyshev polynomials, those roots are always real. But yeah, no, you can't. The orthogonal polynomial. There's some ways in which when you set up orthogonal polynomials, you can guarantee you have real roots. All right, so but that's the idea. So we're going to construct these n+1 orthogonal polynomials. We're going to compute the roots of the nth order polynomial so that c of n of xi is equal to 0. We'll solve the linear system for the weights, and then we'll approximate the integral as the sum. All right, so it's a great method, and you have a lot of degrees of freedom about how you do the orthogonal polynomials, because we use just one definition of orthogonality. But you can come up with all sorts of different schemes by changing what we mean by an orthogonal polynomial. So that says the inner product of two polynomials integrated over the integral is 0. We could pick different intervals. We could pick a weighting function that sits in the middle of it. And you get things like Gauss-Lobato, Gauss-Chebyshev, Gauss-Legendre, all these different ones that have to do with different intervals and different representations of the inner product. But they all come down to the same thing. You have to find the roots of the orthogonal polynomials, but you get to play with what orthogonality is, or to come up with a sort of weighted orthogonality. So an n-point Gauss quadrature method is exact for polynomials up to order 2n minus 1. And that means the thing goes what we refer to as spectrally accurate. And that's how you get the meaning that is you add more points. If we're looking at something like the simple quadrature scheme of using the midpoint rule, this one has an error that's proportional to 1 over n squared. If I double the number of points, I'll get something like 4 times as much accuracy, or 4 times reduction of the error. But these methods are much more accurate. Now we come back to the point I put up at the beginning, at the earlier, which is this is doing the cosine. This is the Gauss, actually the Gauss Chebyshev is the one I use for here. Even though this is Gauss quadrature, it's using Chebyshev polynomials, which look a little like sines and cosines. And I would just remind you that with 11 points you can get machine precision out of these methods, and you can almost see that each time the lower you add 1 more point, you get errors that is double on each additional point. So that's that characteristic of spectral accuracy. So any linear accuracy will give you a straight line on a log-log curve, and spectral accuracy means it's going down, so it's going even faster than a straight line. There's no straight line with any slope that will fit. Then another thing to look at is, well, suppose we took this interval from -1 to 1 and looked to see where the simple quadrature points are, midpoints of each of these intervals are, versus the Gauss quad points. You could look at it and say, well, they're not that different. But they are. You can see, and this is what's characteristic of many of these quadrature schemes. Notice they're squeezed together at the ends and spread out in the middle. So it's a small, it looks like a small thing. I mean, you're moving them around. And the weights are not that non-uniform either. I didn't plot them, but they don't change that much. But when we're talking about these high accuracy calculations, these kinds of small differences make an enormous difference. And we're not looking to get 1% accuracy or 0.1% accuracy. If you are, then midpoint rule is fine. If you're looking for much higher accuracy, close to machine precision, then these things make an enormous amount of difference. And even small changes like this point placement and the changes in the weights can make an enormous difference. All right, so we talked about this Gauss quadrature scheme, and these are great methods. And we're going to see next time the reason we're looking at them is because we can actually turn them into a method for solving integral equations in some settings. But not all of them, and not the most common one in 3D, which are these panel methods I talked about in the first lecture. So remember what our problem was for a panel method. We're calculating these panels under which we're going to assume a constant density. And if we're doing a collocation method or a Galerkin method, we have to calculate these integrals of 1 over distance over this panel for a point on the panel, which means somewhere in that panel, the integrand goes to infinity. This is what's called a singular integral. And we knew from last time we knew it was an integrable singularity, and we did that by carving out a disk out of it to prove it. But for this problem, those quadrature schemes aren't going to help. So, and I want to show you what happens here. So if we do something like 1 over the square root of the absolute value of x and try to do a quadrature scheme, as long as we keep away from the quadrature points at exactly x equals 0, we can still formally do the quadrature, no points at x equals 0. So we have to pick up a polynomial that gives us, for whom the root is not 0. But we don't get very good convergence. That is, and the reason we don't is this thing goes off to infinity. But I want to make a point about the difference between two types of infinity. So there's 1 over the square root of absolute value of x versus 1 over x. All right, so the 1 over the square root of the absolute value of x, that is an integrable singularity. The area under the curve is finite, even though the integrand goes to infinity. And the 1 over x case in one dimension, that goes to infinity. Now, it doesn't go to infinity in 2 dimensions, but it doesn't in 1D. There's no quadrature scheme that can give you, that can solve this problem, right? If your integral is infinity, here's your integral, infinity. That's it. Right? You're not going to be able to do anything else. If it has an integrable singularity, then maybe a quadrature scheme would help you, except what's true about that problem? When we started doing these quadrature error estimates, what thing did we count on in order to say something about the error? We used the remainder theorem for the Taylor series, which counted on what about the derivatives? Right, it was the Taylor series expansion of derivatives? Yeah.
They can't go to infinity.
Yeah, but the derivatives of the integrand are going to infinity. Right, all those quadrature estimates of the error, they're pretty much worthless here. So you might say, well, okay, so we spent a class on these quadrature schemes, and then at the end of the class I tell you, for the integrals you most likely see when you're doing these integral equation methods, you can't use these schemes. Right. Well, that's not entirely true, because there's only one panel you have to worry about, right? The panel with the test point on the panel. All the other panels that interact with this panel, you can do those with quadrature, and it works great there. So if I have a discretization with n panels, then I've got to do n squared interactions, and only order n of them is problematic. So you can do Gauss quadrature and do a great job of n squared minus n of the panels, and the n panels that you can't do that with, you have to do something else. So I told you something, so if n is very large, like 1,000, then n squared is 1,000,000, and n squared minus n is almost 1,000,000. So I'm telling you something that works better than 99% of the time, and that should be good enough. But of course, if you have to solve these problems, you're still stuck with this, what to do for the self-term. So the problem is that simple quadrature done on these problems that have singular integrands are usually better than Gauss quadrature. Doing the special placement of points and weights, it doesn't help you at all in the setting. You need to do something else. All right, so I'm going to take a little time at the end, and I'm going to talk a little bit about what people do now, but I want to show you some of the things, the standard things people try. All right, so here's one way of dealing with the problem. You say, okay, well, look, I can do Gauss quadrature. So if I imagine I have a panel and I want to, no, I have this. All right, so imagine this is my panel, and I want to integrate 1 over r, and the problem is that the 1 over distance on the panel, it goes to infinity at the center. So I'm going to do my Gauss quadrature scheme on this region, and then I'll do something else in the interior. And I might, because it's hard to do this region, I could tear out a square out of it, so it has, the geometry is nice, and I can do Gauss quadrature on these nice square intervals, so it's easy to do. So all right, that's better. I just have to pull out, I just have to figure out what to do with this little square in the center. And I say, well, okay, but I haven't removed the problem. I just figured, well, look, it's a much smaller contribution to the integral, so if I screw it up, it won't have as bad an impact. You say, well, okay, but you're still screwing it up. So you take this one and you say, all right, well, I blow this square up into another square and I take out a little piece. So I start by taking out one piece, and then I go inside and take out another piece and another piece. And you do that a few times. These are sometimes called refinement strategies. So people do this kind of thing, where they try to deal with the singularity by taking out smaller and smaller regions of the domain you're trying to integrate, and do the rest of it with the regular quadrature scheme, and really just the region right around the singularity with something else, or with a low order scheme. So those work all right. They're not great, and they're often pretty expensive. The other one that's very popular is find the change of variables. So sometimes, if you know what the function is, maybe the change of variables, if you put the integral in terms of the change of variables, then you get rid of the singularity. So that's really popular too. Though, if your function that you're trying to integrate, if you come up with that change of variables, great. Turns out 1 over r, 1 over distance. No, there's no nice change of variables that will do that. But there are some things you can do. So you have all these kinds of schemes, and if you go through the literature, you can find literally thousands of papers where they say, okay, we're going to do a quadrature scheme where we're going to use polynomials with an inner product where the singularity is in the inner product definition, and that's going to work for this kind of singularity. And there's some papers that can deal with singularities that correspond to a point in the center, and one at a point at the corner, and one at a point along the edge. They have all these different things that you can do. And it turned out that there's something else you can do in that case. So I'm going to show you a picture of what you do. So let's imagine that we're doing this integral from 0 to 1 of 1 over the square root of the absolute value of x dx. And we know if we plot that 1 over the square root of the absolute value of x as a function of x, when x is large, it's fine. Because as x is bigger, it goes down slowly, and it blows up near the origin. So this is our problem, right, at x equals 0. So we don't care about the rest of this interval. We want to do something about this. So the idea is to come up with, so we'll call this f. And we're going to come up with a new integral, which is going to be integrated from, instead of from 0 to 1, it's going to go from minus infinity to 1. Well, actually, they usually do ones that go from minus infinity to plus infinity, where you're going to come up with some function g of t, and we'll use the change of variables formula, where g of t is going to be when t is equal to infinity, g of t equals 1, and when t is equal to minus infinity, g of t is equal to minus 1. So we're going to take this function, and we're going to try to expand it out over this infinite domain. We're now going to have it go from minus infinity to infinity, so that we put this thing that's going off to infinity out at the infinite interval, and you might think, well, what the heck is this going to buy? So we now have this problem of we've replaced this integral from 0 to 1 with an integral from minus infinity to infinity. So you look at that and you think, well, that can't possibly be a good idea. And it turns out and I'll put a reference on it because these have become very popular methods now. That if you have a function that looks like that, as long as this function g prime of t goes to 0 faster than your original function goes to infinity, that the product of f of g of t times g prime of t, you can arrange for it to look like this as we go from minus infinity to infinity. So if we look at this function as a function of t, if you can arrange it so that this thing goes to 0 smoothly, it has to go to 0 fast and infinitely differentiable. So you know what these functions look like? They're hyperbolic sines and cosines and tangents. One of those things you learned in high school geometry, you thought, well, I'm never going to use those again. They're back. So you can come up with functions that will do this. For any singularity you come up with, you can come up with something that will, on the minus infinity to infinity interval, will go to 0 smoothly and fast enough so that it will go to 0, the product of these two terms will go to 0 faster than f is going to infinity. And you might say, well, wait a second, now I have to integrate from minus infinity to infinity. So how do I do equally spaced points from minus infinity to infinity? Well, I can do midpoint rule, I can put one at 0. That's one point. Where's the bisect the next interval? So what you do is you look and say, well, I don't care about the tails anymore. And then you just put points in, and it turns out you can actually use equally spaced methods for reasons I'm not going to go into. But you just put points down, you figure out how much of the tail you're willing to ignore, depending on what precision you need, and then you spread equally spaced points over the rest of the interval, or you do your Gauss quadrature points, or do whatever you want in that interval, because in this interval, everything's smooth. Nothing goes to infinity. And you might think, how could that possibly be the best way to do it? And it turns out, when you try all these schemes for putting down points and weights, the best thing to do is to come up with these mapping functions that are infinitely differentiable. Things like e to the minus t squared, the error function, or that's the derivative of the error function, or hyperbolic sines, cosines, and tangents. You can use to construct these things. And that's what most of the good quadrature schemes that deal with the singularity are. It seems very counterintuitive at the beginning, which is why only recently it has become popular. Because you think, how could that be the right way to do it? But when you're done, you end up with methods that use a few dozen points and can do these singular integrals incredibly efficiently. Yeah, I'm sorry, it looked like you had a question. No, no,
No.
So I'm going to stop there. I wanted to sort of throw this in at the end because it's only in the last few years that these methods have started to become popular. And I'm afraid, I fell into that same category of people who said, no, come on, we're not really going to take an integral from 0 to 1 and turn it into 1 from minus infinity to infinity. That can't be a good idea. But as people have gone through and made practical implementations of these methods, and you look at the number of points in which you have to use and how general they can be developed, you find that they're quite effective methods, and they're now good pieces of software that can do these kinds of transformations and let you do singular integrals. Though you do have to arrange to put the point where the singularity is at the end of your integral. So if we have a panel and we have a singularity in the center, we've got to break it up into 4 panels so that the singularity can be at the corner. So there's some issues that I wanted to at least show you this, and I'll put a pointer to one of the papers that gives a good survey of these kinds of methods and pointers to software so you can see. But I wanted to show you at least at the end of this that there are ways of dealing with singular integrals. But what we're going to do next time is look at problems for which we don't get singular integrals, and we'll do that next time. But for this, I just wanted to show you, what's the most modern thing, even if we did it sort of vaguely at the end. But the big thing to remember about orthogonal polynomials and this idea of points and weights, where the points are coming from a polynomial, the zeros of a polynomial, and the weights are coming from solving a linear system. These are very powerful techniques. You can often construct very effective quadrature schemes for yourself by discerning what's a good set of polynomials to use for your own problem. And as we'll see next time, it also helps you design very good methods for solving integral equations in 2D on closed curve boundaries. All right. What I didn't talk about is multiple dimensions, and I wasn't going to say too much about that because we won't be doing much with that next time. But if you ask, I'll talk about it a little bit, maybe towards the end of this last week of the term. All right. So let me stop there. The video I know I'm late on should be up by tomorrow, I think, for last class, and will be up for this class hopefully another day after that. And there'll be a problem set that will be posted, and we're negotiating about what times to do these evening problem set sessions. But you should come to one or the other of them and plan on starting and finishing the problem set in that session. This is not supposed to be, it's supposed to be a chance for you to try working out a problem that gives you an idea of how to use these methods, not to, then make sure that you sort of have a sense of where the material is. We just didn't have enough time in this last part of the course to give you the opportunity to sort of let it sink in so we can do something. We want you to see actual practical calculations, but we don't have enough time. We can't give you enough time to actually think this through without being able to ask questions. So please, as you're thinking about the problem set when it comes out, think about coming to one of these sessions. I think you'll find it's a good experience, and if you try to do it on your own, there are probably things that you needed to know that we haven't told you, or we assumed you knew that having come to the evening lecture would have saved you from frustration. So please, as you're thinking about that. And then I think they're going to use the last couple of minutes. I think Professor Wayne will talk a little bit about the projects. So I'm going to hand it over to you. I'll stop there. And again, video in a little bit.
Yeah, so I think consider the time constraint we have.